Right, so today we are going to jump into chapter 5. We are bypassing, we're just going to jump into chapter 5. We are going to be looking today at exponential expressions. Now, I will be completely honest. I love exponents. I love exponents. I love logarithms. We're going to talk a little bit about both in this class, but we're really going to spend some time here today on exponential expressions. So this is kind of like the very beginning of exponents and looking at how they function and work all together. So what I did was, if you look at the textbook, there's a whole bunch of different examples as well as all the rules, and they're all kind of all over the place in the textbook. So I decided to put them all in one place. And so these are, again, just the basic rules that'll come in handy. And I just want to briefly go through them real quick, and then we'll go into a whole... I literally have so many examples that I just want to show you. They're just fun, and they're pretty easy once you get the hang of it. So we're going to go through a bunch of those here today as well. So let's go ahead and take a look. We've got the rules of exponents are kind of tied together in a really unique way. So here, when we're multiplying two different exponents that have the same base, we're actually going to add the exponents together. So it's kind of weird. When you have multiplication, you're adding. And then down below, this is a little further down, but we'll come to it here in a few minutes. But when you're dividing, you're actually subtracting. So division and subtraction are connected with the exponents, and then up here, multiplication and adding are connected. Let's look at the second one here. So if I've got x raised to a power, and then I'm raising that to a power, I'm actually multiplying these two values together, the m and the n. Same idea here. All that I'm going to do in this case is I'm going to distribute the p to both the m and the n. So this ultimately becomes x times m to the p, y times n. X times mp times y times np. Okay, that's kind of hard to say. Essentially, the p is multiplying by both the m and the n, and the bases are going to stay the same. So when I say base, I'm meaning the thing that the exponent is raising. Okay? The exponent is the thing that the base is being raised to. So I just mentioned how when you divide, it actually is subtracting the exponents. X to the 0 is equal to 1. That means actually anything that you raise to the 0 power is always going to equal 1. All the time, no matter what. You're always going to have 1 when you are raising the whatever base you have times up to the 0th power. Quick note, we do not define 0 to the 0. In other words, it's literally undefined. We just do not have it defined in mathematics. Another cool property here is that if you have a negative exponent, you can actually flip it into a denominator and make it positive. Okay, so you're just changing the location of it and changing the sign. This comes in handy in a lot of different cases. For those of you who are going to college algebra and calculus, specifically in calculus, is really, really helpful tool here. Same thing if you have something that's a negative in the denominator, you can flip it, make it positive in the numerator. So really that property is just saying I can move it between a fraction and not a fraction just by making the exponent negative. Okay? And then same property that we had up here is basically the same here with a fraction. So that p is going to distribute to x to the m and y to the n, and that is multiplying times that exponent. Okay. Scientific notation, this actually shows up in a lot of places, specifically in when you're dealing with really, 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 really small things or really, 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 really big things. So I say it's a more convenient way to read very large numbers, or very small, I should say, as well. So this is what scientific notation looks like. Okay, you've got a number here, and the way I define it is that it's between 1 and 10. it can't equal 10, so you can have like 9.9 times 10 to a power. Really the big thing that you're looking for is that the number is somewhere between 1 and 10, okay, but not equal to 10. So when you do that, you can actually represent it as something different, because it's a lot easier to write something in scientific notation than it is to write something with 30 zeros, right? And you lose track, you can't keep count, it's just a pain in the butt. So pretty much this is just a really handy way of keeping track of really big and really small numbers without having to write out a whole bunch of zeros. Okay, so let's go ahead and flip over to the board. We're going to go through a whole bunch of examples, and hopefully this stuff makes sense. Like I said, I've got a lot of examples, so this hopefully will be really, really, really helpful video for you guys as you're going through it. Okay, so let's do question 12. And this is telling us to do 5x squared y to the 4th times 3y squared z to the 3rd. Okay? So because we're multiplying all these things together, what we need to do is let's do each piece separately. So we'll multiply the coefficients times each other. So 5 times 3. Okay, I'm just going to rewrite it in a convenient order. We look at both and we notice that there's only an x squared here, or an x I should say, in this specific piece. There's no x over here. So I'll just write x squared. There's a y to the 4th and a y squared. So this is going to become y to the 4th times y squared times, these are all multiplying by the way. And there's no z here, but there is a z here, so this becomes z to the 3rd. Okay? So now we can actually simplify this even further. Let's combine 5 times 3. This is going to be 15. The x squared is coming for the ride. And then notice I've got two of the same base, but different exponents. And since they're multiplying, that means I've got 4 plus 2. Okay? Times z to the 3rd. Okay? So this means that this is equal to 15x squared, y to the 6th, z to the 3rd. And this guy right here is my final answer. Okay? That is fully simplified. So what you can see, let's just draw some comparisons here between these two, what we got at the very end and what we got at the beginning. You multiply the numbers. If you have any numbers in front, you just multiply them together. And then what you're doing is you're looking for what's common between both pieces. So there's only an x squared there, so the x squared is going to follow along. A y to the 4th and a y squared, which means those two are going to add. We're going to add the exponents. And then the z to the 3rd. And that's, again, because all of these are multiplying, this is what we ultimately get. Okay? Question 14. So this is z to the 3rd all raised to the 4th power. Okay, so remember, again, you can go back to the rule if you need to remind yourself of what it is. So now this is a situation that is like this guy right here. Okay, so what we do when we have something like this raised to the 4th power, let me actually write it out so you can see what it looks like. This is the same as z to the 3rd times z to the 3rd times z to the 3rd times z to the 3rd, which is equal to 3, 6, 9, 12, z to the 12th. Okay? Or, again, the other way you can do it, if you did it from the way that the notes describe it that I posted earlier, z to the 3 times 4, right? And that also is equal to z to the 12. This is kind of like the explained way of writing it out that I just wanted to show you. All right, so let's do question 18. We've got r to the 3rd times s all raised to the 5th power. Okay, so now that's the same as since we've got two different bases that have exponents. If you have an s here, you can think of this as being like a 1, an s to the first. Okay? So remember from the rule, this is going to be r to the 3 times 5 times s to the 1 times 5. Okay? Because again, both of these things are being raised to the 5th power. So now this becomes r to the 15, s to the 5th. And that right there is our final answer. I think I didn't box that one up above either. All right, so those are our three solutions to those problems, okay? Let's go ahead and keep going. Like I said, I got a whole bunch of examples, so hopefully this will help you on your homework. Let's do 36. This one's a little trickier. Here we've got 2 times a squared b, all raised to the 3rd power, times minus 3 a b to the 4th raised to the 2nd power. Okay? So again, let's go ahead and just write all of this out. The first thing that we're going to do is we don't want things that have exponents. We got a whole bunch of stuff raised to the 2nd power. So let's actually distribute this 3 to every single, the exponent to everything that's in that parentheses. Now the interesting thing is that because we have a 2 here, the 2 is also being raised to the 3rd power. Everything inside is getting raised to the 3rd power. So here, this would become 2 to the 3rd power. Okay. We have a squared to the 3rd, so this is a to the 2nd times 3. And then we have b to the 3rd. Okay? And now we are going to multiply the second piece. Same idea. The minus 3 is being raised to the 2nd power. Okay? So don't forget, this is different than, so let me write it down because it sounds exactly the same if I were to say it. This is not the same as minus 3 squared. Okay? Because here this is equal to 9, here this is equal to a minus 9. Okay? The way you can think of it, this minus sign is describing 3 squared. So it's a minus 3 squared, which is a minus 9. Here, the minus is actually getting squared as well, so this is why it becomes positive. So that, again, big distinguishment there. It's important to remember that. So here we're going to have a squared, and then we're going to have b to the 4 times 2. Okay? So now 2 to the 3rd is going to be 8. This is going to be a to the 6th, b to the 3rd, times minus 3 squared is going to be 9. A squared, that follows along, b to the 4th, or sorry, to the 8th. Okay, we're getting there. Now we actually are back at similar to what we had question 12. Let's just write out all the individual pieces. We have 8 times 9 times a to the 6th times a to the 2 times b to the 3rd times b to the 8th. Okay? So that means we have 8 times 9 is 72. A to the 6th plus 2. B to the 3 plus 8. Again, we're adding because, again, this, remember, multiplication, adding is the same as adding, okay? So 72, a to the 8th, b to the 8 plus 3 is going to be 11. And this right here is our final answer. Okay. So again, we're merging a whole bunch of stuff together all at the same time. And the trick in doing this is just to try to follow the process and the rules as much as possible. In fact, it might not be a bad idea to actually just have those rules handy in front of you when you're looking at these, just to kind of recall to your memory what you need to use. All right, let's look at 46. x to the 5th, x to the, this is x to the 5th, y to the 10th, all over x squared y, okay? So now we're getting to the section where we have fractions. So if we go back to the notes real quick, when we have fractions of the same base, we're actually subtracting the exponents. So if I were to look at this problem, we're going to do each individual base on their own. So here, this would be x to the 5th minus 2. X to the 5 minus 2. And then the same idea here, the 1, if there's no exponent, it's assumed to be a 1. This means that this is going to be y to the 10 minus 1. Okay? So now, I just do those operations. 5 minus 2 is going to be 3. 10 minus 1 is going to be 9. And that right there is our final answer. Let's do 54. 1 over x to the minus 4. This is equal to, again, going back to the rule. I keep going back to these notes because they do really come in handy. Remember, if I've got something where there's a negative sign as an exponent, I flip it into the numerator or denominator depending on where it is. So down here, this is in the denominator, so I flip it to the numerator. Now, in this question, this is the same idea. We have x to the minus 4, which means that I negate the sign, and it just becomes x to the 4th. And that's literally it. It's just a one-step problem. Okay. 58. So now here we've got x to the minus 4 times x to the positive 4, and we need to solve this. Now, one thing that you can do is you can ignore the, well, actually, let's just go ahead and do this. If I have x to the 4th over x to the 4, because I'm taking this and I'm bringing it down into the denominator, right, and making it positive, then I have, again, if I'm simplifying this, x to the 4 minus 4, which is equal to 0. Oh, sorry, it's equal to 1. Oh my gosh. X to the 0, it's equal to x to the 0, which is equal to 1. Okay, there we go. So here I did the conversion between a negative and bringing it down into the denominator. However, since these two are multiplied right here, what you could do is the same thing. You could do x minus 4 plus 4. Okay? This is also equal to x to the 0, which is equal to 1. So you could do it a couple different ways here to get to the same final answer, which is 1 in this case. Both ways will work perfectly fine. But again, it's however you want to approach it. All right, let's keep moving on. So that was 58. Let's look at 66. Here we've got x squared times y to the minus 4 squared. Okay, sometimes it is actually advantageous for us to not put it in the denominator. You can keep your y to the minus 4 here just like this, and then distribute that 2. So here we get x to the 2 times 2, y to the minus 4 times 2, and then this is going to equal x to the 4, y to the minus 8. Now, personally, I prefer to make it so just I'm multiplying. Sometimes dividing is kind of annoying and subtracting. I just prefer the multiplication, which is adding in when you're dealing with exponents. So now, once we get to this point, y to the minus 8, that actually means that we flip it, we change the sign, and we take it into the denominator. So the x to the 4th is going to stay the same. We're not going to move it. It's going to stay up in the numerator. And then this becomes y to the positive 8th. Okay? So again, anytime you see a negative, you just flip it and bring it into the denominator. When you see a positive, you could if you want, you could flip it and make it into the denominator as well. You just change the sign. So this is how you would go about solving one of these problems. Okay. All right, let's keep going. We're gonna do a few more, and I'm gonna do a scientific notation one as well. Actually, I think that's. Let me see here. Yeah, I'm gonna do 2 or 3 scientific notation questions just so you can see how they work. Let's do question 70. So x to the minus 2 y squared times xy to the minus 2. Okay. Now I always suggest distributing the minus 2 and the 2 in each piece. So we're going to keep it multiplying. X to the minus 2 times 2, y to the 2, and then we're multiplying times x to the minus 2, y to the minus 2. Whoa, that's a weird y. Hello. Y to the minus 2. Okay. So now let's simplify this. This is going to become x to the minus 2 times 2 is minus 4, y to the 2, and we are multiplying by x to the minus 2, y to the minus 2. Okay? So this becomes, well, now we are multiplying. So let's just do them in order. X to the minus 4 plus a minus 2. Okay? Y to the 2 plus a minus 2. Okay? Or we can just say instead of plus and minus, we can just subtract, because it's the same thing. So this is going to be a minus 2, this is going to be a minus 2. Okay, so now x to the minus 4 minus 2 is x to the minus 6. This is going to be y to the 2 minus 2, which is y to the 0. And now, since y to the 0 is equal to 1, I have x to the minus 6. Now I can take this and take it into the denominator and just flip the sign. X to the 6th. So that is actually my final answer for this problem. Okay. All right, let's go ahead and look at a couple of scientific notation questions. So what we're going to do for the first one is convert a decimal into scientific notation. So 92, we have 0.000, I gotta get the right numbers, 1, 2, 3, 4, 5, 5 zeros, 4, 6, 7. See, this is why it's annoying. This is why writing out these full numbers is annoying, and we can represent it as scientific notation in a much easier way. Okay, so quick note. This is important. Write it down. Keep an eye on this. And of course my camera turns off, so now you can't see it. Hang on, it's coming back. I promise. Okay, here we go. So the quick note. If you are starting with a decimal, the exponent is negative. Okay? If a really big number the exponent is positive. You guessed it. So, and of course I'm a little off the screen. There we go. So if I'm starting with a decimal, the exponent's going to be negative. If I'm got a really big number, the exponent's positive. This right here, I'm starting with a decimal, okay? And all I need to do when I'm putting things into scientific notation is literally just count the decimal places that I'm moving. So here, remember, for scientific notation, the very first number that we're looking at, it has to be a number between 1 and 10. So that means that the decimal place is going to have to be put right there. Okay? So that means that I've got 4.67, since this number is between 1 and 10, and all I have to do is count how many places I moved the decimal. So 1, 2, 3, 4, 5, 6. Okay, I moved it 6 places. Now, because this was a decimal when I started, it's going to be a -6. Okay? That's it. Now, if I do the opposite, let's look at 96. Okay? A lot of times people make scientific notation a lot more complicated than it has to be. Does anybody know what this number is? Here's hundreds, thousands, millions, billions. 200 billion. Okay? So, the number between 1 and 10, in this case, is going to be 2, which means the decimal place is going to go here. So we're going to have 2 times 10 to the, how many decimal places did it move? Well, notice the decimal is going to be right here, and we have to just count from here all the way over to there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 10 to the 11 power. Okay? That is all we are doing with scientific notation. So again, because this is a positive number, it's big, it's huge, that means that the exponent has to also be positive as well. Small numbers that are decimals that you're converting to scientific notation will always have a negative sign. So it's kind of the difference between the two. So that's it for question 96. Now let's go ahead and jump into the very last one. We're going to actually convert this one from scientific notation into regular notation. Okay? 3.9 times 10 to the minus 2. So, what I'm doing is I'm going to start with my digits, which is 3, 9, and I'm moving it. In this case, since this is negative, that means that the decimal itself, or my original, is going to be a decimal. So now, to get a decimal, I need to move it 2 places to the left. So, move it 1, move it 2. And notice there's nothing in that place, so you put a 0. So the answer is literally just going to be 0.039. Okay? Well, that's it. That's section 5.1. We looked at exponents, we looked at scientific notation, some of the properties, and yeah, I mean, that's pretty much it for this lesson. The next time we're going to take a look at section 5.3 and it's polynomials. Hopefully this will be some review for you. If not, then we should have a fun time. But that's all for now, and otherwise enjoy.